So now that we've discussed how semaphores work, we're going to talk about some usage considerations to keep in the back of your mind when you apply them in practice. So Semaphore is a lot more flexible than other Java synchronizers, in particular reentrant locks. We haven't talked about reentrant locks in detail yet, but we will. That is clearly not really me. I don't think I was ever that flexible. I'm certainly not that flexible anymore. But the power of Photoshop can make you do amazing things, or make it look like you're doing amazing things. So with respect to synchronized statements, which we'll talk more about later, that's the synchronized keyword. With respect to reentrant lock, which we'll also talk a bit more about later, those are all fully bracketed. And semaphores can do more things than those simpler synchronizers. One of the things you can do is of course, you can atomically acquire and release multiple permits with a single operation, so you can get multiple things, kind of like beaming down the away team on Star Trek. You can do them all in one fell shot, one fell swoop. Whereas with synchronized statements and reentrant locks, you can have one thread acquire, one thread release. Likewise, semaphores, unlike synchronized statements, unlike reentrant locks, are not restricted to being fully bracketed. You can do that kind of ping-pong approach that we've talked about. On the other hand, there's a cost for this extra flexibility, and the cost is it's a little bit more expensive to do these more powerful operations. So if you're just trying to provide synchronization, if you're just trying to protect a critical section from concurrent access, stick with reentrant locks, stick with synchronized statements. But if you're trying to do something more powerful, then semaphore might be for you. When a semaphore is used to track, or is used to be guarding access or mediating access to a resource pool, it tracks the number of available resources. That's what the count is explicitly doing. In fact, if you think about your Palantir Manager example, that's precisely what it does. It tracks the number of these things. However, it doesn't track which resources are free. So you have to figure out what resources are free. And in order to do that, you're going to need some other kind of data structure, like a hash map or a list or a set or whatever it is that you need in order to do that kind of stuff. So that's why in our program, in the Palantir simulator program, we use the semaphore to keep track of how many Palantir are available or not. But then we also have this separate data structure, the hash map. And keep in mind that that hash map may need to be protected by synchronizers in order to ensure that its thread's safe. So there's really sort of two things going on. The semaphore is being used to keep track of the count, and then we have some other data structure with some other synchronization mechanism or synchronizer that's being used to actually guard access to that thing. Now, in our particular case, we're using a hash map, and therefore it does not have protection, but you can provide protection through some other synchronizer, like a spin lock, as you're doing. For other data structures that are part of Java, like a concurrent hash map, synchronizers are built in to the data structure itself. And we'll get to that later in the course. One of the tricky parts with semaphores, with reentrant locks, with condition objects, with reentrant read-write locks, with stamped locks, and all these good things, is that they are very low level. And as a consequence, they can be somewhat tedious and error-prone to program due to common traps and pitfalls. And you'll see when we talk about reentrant lock and reentrant read-write lock, we'll see similar problems arise there. One problem is holding a semaphore for a really long time without releasing it, thereby keeping others at bay or starving others out from getting anything useful done. So here's a very simple example where we have a semaphore. It starts out with a count of 1, so it's available. It's a binary semaphore. And we have some method, and we come and we acquire the semaphore, and then we do some very long-running operation that may not involve the semaphore, right? So it doesn't really have to be locked. And we don't actually unlock the semaphore till we're all done with that very long operation. And what that means is that other threads are unable to get in to do their work while the semaphore is being held. So the key thing to remember, and this is sort of important with semaphores, it's really important with other synchronizers like reentrant lock and so on. make sure you only hold them the minimum amount of time they need to be held, because they're keeping others at bay. So it'd be kind of like, it's kind of a strange analogy. It's kind of like someone goes into a restroom on an airplane and then decides to have a conference call, right? You know, they've got the door locked. They don't really need to be in there. They're not using the restroom for the purpose it's intended, and they're just chewing up everybody else's time. In fact, I was going to use a Seinfeld reference, but it's probably not worth it. Another problem is to release the semaphore more times than you ought to. And here's an example where we acquire the semaphore once, and then for some bizarre reason, pilot error, didn't get enough sleep, whatever, malicious attempt to circumvent the locking protocol in the program, the semaphore is released multiple times. And these extra calls to release will allow the count to go much higher than perhaps we intended. Notice it started out here with a count of 1, and now it's a count of 3 after we call release multiple times. Actually, I think it's a count of 2. Yeah, it's a count of 2. And as a consequence, we have the semaphore in some bizarre state. So we don't want to do that. Yet another problem, this is why it's so important to use try finally. You can acquire a semaphore and then forget to release it if it was intended to be fully bracketed. Now, of course, if it wasn't intended to be fully bracketed, this may be perfectly fine. But you'll notice here, we come in, we acquire the semaphore, then we do something or other, and then we return. And we forgot to release it. Let's assume it was intended to be fully bracketed. So that, of course, will cause problems, because now that semaphore is acquired and nobody else can get in there. And this is the reason why you should always use the try finally idiom to obtain these locks if they're intended to be fully bracketed, because no matter what happens, whether you return or you break or whatever happens, an exception is thrown, the synchronizer will be released. And I'll be really pushing you hard on that. So here's the advice so that I don't have to type this as many times in my reviews. Make sure you always use these synchronizers when they're intended to be fully bracketed in try finally blocks. So make sure you always release stuff. And that applies both for the semaphore and for the spin lock and so on. Another problem with semaphores is they're actually rather limited. All they do is keep a count. It goes up and down. And so if you have more complicated coordination use cases, they may be more trouble than it's worth. And in some situations, as we will see as we get further along in the course, other synchronizers, particularly other more sophisticated coordination synchronizers, coordination-oriented synchronizers, like Java condition objects, may be a better choice for complex use cases. And we'll also be talking about those things, obviously, very soon.